Hi, everyone. I work with the automation products, but I'll also briefly touch on some of the security products offered to ADI. Today's webinar is going to be highly focused on a hot topic, which is elevated skin temperature screening, also known as elevated body temperature screening. We changed the name, I guess, from body temperature to skin temperature because I guess body is kind of a misnomer when you think of scanning an entire body because we're really just looking at the surface temperature or the skin temperature of someone's face. But without further introduction, I'll go on to the next slide. So a little bit about FLIR, our global company. As mentioned by Michael, thank you. We're actually produced most of our products in either Estonia or Sweden. Most of the A series that you're going to see are actually produced in Sweden. We generate around 1.8 billion in revenue a year, and only 59% of that is actually thermal. But we have been producing thermal imaging since, I believe, 1968. So we're one of the oldest and longest provider of infrared technology. We have around 4,200 employees worldwide and serve about 173 countries. Here's a cool little spectrum of the electromagnetic spectrum. Over on the left, you've got shorter wavelengths, which are characterized by higher energy. And then there's our infrared spectrum, a little behind, a little longer than visible light. And then you have even longer waves, which are microwave or radio. Could you please make sure that everyone is on mute so we can help with the broadcast? And here are some of the things that we've done with infrared lighting. So that's either measured temperature for critical asset monitoring, you can see through fog and smoke for firefighters, and you can see in complete darkness without light, which is very nice. So there's been a lot of questions lately. What products are actually available to ADI? So I'm going to go over a brief overview. If you do have more questions, maybe ask your local branch manager, and hopefully they can provide you a price list, or feel free to reach out to myself or someone else at FLIR to ask what parts are available. But in general, I mean, you have a ton of security products, so I don't have them all listed, but the SAROs, the DX series, they're all listed on the left here. There are quite a few security products, so these are just some of the more commonly used ones. And then on the automation side, which is any camera that starts with an A, which are probably going to be more used for this elevated screening temperature, or sorry, elevated skin temperature application, are going to be the ones in the A. So A400, A700, A310, and as you can see, the rest on the automation side. I'm not going to go too much into product detail, more application detail, but maybe we can have a follow-up meeting to go over the functionality of these cameras outside of elevated skin temperature monitoring. So some of the applications used with the A series or the automation are critical asset monitoring. So if you can think of any process where the equipment needs to be monitored 24/7, it's so crucial that this equipment doesn't fail. If it does fail, the company could lose tens of thousands, hundreds of thousands of dollars over a course of hours, minutes, maybe days. And those might include transformers, turbines, computer servers, some electronic drives, right? Maybe a little circuit board actually runs an entire production line because it does the controls. So if that thing fails and it's not monitored for a short circuit or an overheating condition, the entire process goes down. Same with belt systems, right? A single belt system might run an entire conveyor belt. And if that one conveyor belt goes down, maybe the whole process goes down. Motors, pumps and valves, steel ladles, there's quite a few critical equipment pieces that can be monitored 24/7 with a thermal camera to prevent outages. So it's for predictive maintenance, outage prevention, and scheduling maintenance of the very, very crucial equipment. Additionally, the fixed thermal cameras, the A series, have been used very often for early fire detection. The idea here is to see heat patterns rise and occur early so that you can either take action or prevent a fire from actually starting. So on the right, we've got a couple examples. One, I believe, is just a field We're monitoring an entire field, and the one up top is actually a chemical plant. But there's more examples of early fire detection on the left. Battery storage. Lithium is a very big early fire detection application right now. Generation plants, T-lines. Maybe you're looking for debris that falls on a T-line or a fallen tree in a forest that can cause an arc flash, and then the entire forest goes up. You don't know. Storage facilities, right? Food can combust, or even recycling plants and forests. There's whatever application you can think of that might catch fire or need value. Early fire detection can be done with these cameras. So just kind of a business sense, if we actually think about these in a sales perspective, Ford loses $25,000 every minute their facility is down. So if you can think critical asset monitoring, if there's anything that they can monitor that prevents their facility from not operating at full function, they're going to save a lot of money having just a simple camera, even if the camera is very expensive in place. The U.S. Fire Association estimates that just in structural loss, you could lose $127 per square foot. That doesn't account for equipment, that doesn't account for assets, that is just in structural loss, or even fines from the EPA because of damage to the environment, right? So if Amazon were to lose, I did this math on my own, a single facility, one of their smaller facilities due to a fire, they'd lose $51 million. Additionally, right, a mine was connected to a substation, and the substation provided power to the mine, and it was the only power source for the mine. Well, if that substation had to go down for a single day, the mine was losing $1 million a day. So any event that you can think of that might have thermal events, you can really monitor that 24/7 and actually save money, even though our cameras are expensive. Save a lot of money, I should say. Security, right? I'm sure you guys are familiar because you have a lot of security integrators with visual security. In night vision, right, you just amplify the visible light, but thermal is very easy to use for perimeter detection, for vehicle and person detection, and there's a lot of things it can offer that visible can't, right? There's going to be a heat signature of the body, which is going to be significantly different no matter what time of day than a visible signature. So all of those security products, you have dome products, you have pan and tilt, you have fixed focus so that you can really do whatever you want with thermal. Typically, our thermal cameras, some of them actually have the ID software, which helps you detect an alarm based on movement of persons or vehicles and decipher the two. Generally, the security products are a lot less expensive than the automation products because they don't need to be thermally tuned to an accurate temperature value, which is what we call radiometric. So that was kind of a brief overview of the products available to ADI and some of the applications they might be used for. We can have another presentation about that later on if you guys are interested, and we actually can go into product details. But I think the most pressing topic right now is elevated temperature scanning. So we're going to get into extreme detail about our products and how they operate in this particular application. So history of FLIR, we've actually been doing elevated, what was called body temperature screening, and now elevated skin temperature screening for many years. We first developed a solution called the A320, which some of you might have heard of. In 2003 is when we used this camera, or a version of it. It wasn't exactly the A320, but it's very similar technology. We were using that during the SARS outbreak. Well, during the SARS outbreak is when we realized we need to get registered with the FDA. So in 2004, we got our first 510K, and we continued to use this technology for other outbreaks, such as the H1N1 in 2009 and the Ebola outbreak in 2014. And now we've adjusted the technology a little bit with our brand new product, the A400 and A700, which got released this April. So we have been doing this a lot longer than most of the new competitors that have emerged during this pandemic. Now, ISO 13154 is highly recommended by the FDA. And what this certification or standard implies is that the most accurate and consistent body temperature measurement can be taken from the canthus of the eye on the surface, right? So as you can see here, that's kind of the tear duct area. It's pointed out by these arrows. where that red is. Now, as you can imagine, this area actually does vary per person. It might be larger for some individuals and it might be smaller for others. Well, to accurately get that, our R&D has recommended that you have a pixel resolution size of no more than 1 millimeter to 2 millimeters by the same, right? So the pixel needs to be very small to identify that region and accurately measure that temperature. So the FDA recommends this, and we also recommend this approach as well, which really constrains the field of view. Generally, in order to get that kind of resolution, you need to be 3 to 6 feet away from an individual, depending on if you have a 320 by 240 resolution camera or a 640 by 480 resolution camera. And the field of view, even when you're that close, 3 to 6 feet, is really anywhere from 3 feet horizontally to 2 feet horizontally. So you might have heard of a lot of crowd scanning solutions. Those can't accurately measure the canthus of the eye, because if the field of view is larger than 3 feet by 2 feet, then you're not going to truly have the pixel size to actually measure the canthus of the eye. Additionally, right, everyone's surface temperature fluctuates. Core temperature, we know medically, is around 98.6, but surface temperature is not the same as core temperature. This is elevated skin temperature screening, right? So of a sample, we took 70 individuals, and the temperature fluctuated about 2 degrees Celsius. You can see some of them were around 36 and some of them were around 34. So there is some inconsistencies with surface temperature. Additionally, that temperature, the surface temperature, can change based on time of day, activity level, were you just running or were you outside, your gender, your ethnicity, your age. There's a lot of factors that come into play when you're actually trying to measure the surface temperature of someone's face. We have a graph here, right, of the perceived temperature of an individual over time. At night, they were around 99, and as they slept, they cooled off, and then in the day, they were pretty constant, but still, there was quite a bit of change. And it's for these reasons, I'll get into how FLIR's system for elevated skin temperature screening actually works. But let's talk about the idea of screening first, right? So signal, let's say the signal is sickness, or that they're elevated. So they could be elevated, and a response, we could get a response. So we'd be hit, all right, that's good. They were elevated and we got a response. Or they could technically be elevated and we actually miss the response. So the camera doesn't realize they're elevated, but they are elevated. Or maybe they aren't elevated, but we get a response. So they appear elevated to the camera, but they're not actually elevated consistent to what their normal temperature profile would be. Or maybe they aren't elevated and there is no response, so we have a correct rejection. And when I say elevated, we don't know exactly if they're elevated, if they are sick, if they do have a disease present or not. That needs to be diagnosed by a medical professional, and that's why I can only say if they're elevated, not if they are sick. But as you can imagine, right, if we are thinking about this as if they are sick or not, they could be sick, have a response, or they could be sick, not be sick, and still have a response. So that's how this graph kind of works. Now, blackbody. There's a lot of people out there discussing blackbodies. Generally, if you don't have a very, very accurate blackbody, it's going to reduce the accuracy of the camera. So general rule of thumb, in order for the blackbody to be an effective calibration technique, and it shouldn't be calibration, it should be live compensation technique, the blackbody is going to have better accuracy, significant better accuracy than the camera. So you're going to have to look for a blackbody that has 0.2C, maybe even 0.1C accuracy. And a blackbody of that caliber is generally very expensive and the lead time is not short, which is why we don't necessarily recommend using a blackbody. But there is a feature in our camera for blackbody correction. So if you put a blackbody in the field of view using the A400, you can specify what the temperature of the blackbody is, and the camera will correct itself towards the temperature of the blackbody. Another reason we don't recommend blackbodies is because then it assumes that you're alarming on a threshold. And as you could see from earlier, people's surface temperatures do fluctuate throughout the day and per person. So if you are alarming on a threshold, you might miss or over alarm. So this is kind of a question that gets asked a lot. Our accuracy of our cameras is 3.6 Fahrenheit, which doesn't sound accurate enough for elevated screening, right? At 3.6 Fahrenheit, if you're setting a threshold of 99 and they could be 96 or 103 based on the accuracy, then how is the camera being used for screening? Well, our cameras are stable. So for instance, if you say there's a 100-degree target and our camera says it's 97, 90% of the time, it's going to say any 100-degree target is within 0.15 Celsius of that value. And 99% of the time is going to say that target, whatever it perceives that temperature to be, is within 0.25 Celsius. So yes, if you look at a 100-degree target, there's a small chance the camera says that it's 97 degrees Fahrenheit. Now, it's going to say that target, though, is 97 consistently throughout the duration of its use. And that's what this graph actually shows you. Over a 14-hour time interval, this is how much our camera varied. And that's where we're saying 90% 0.15 and 99% 0.25. It's very, very stable. And that is how we actually use our screening mode. So now that I've talked about a black body and threshold alarming, and I've talked about the inconsistencies with individuals' faces and how they can change throughout the day, it'll make more sense how our screening mode works. So our screening mode actually samples 10 individuals at a time, and it takes the average maximum temperature of their face. So right here you can see on the right, you draw a region of interest, like a box, and it will automatically find the hottest point in the picture. When you find once it finds the hottest point in the picture, the maximum value, it takes that value and it averages that with 10 other individuals. So if the average temperature for, let's say, 11 o'clock in the day is 96, then we'll alarm off of a deviation. So we always set a set deviation. In this example, we can see that the sample average is 97 and the deviation is 4 degrees Fahrenheit. So if whatever the average is, we're going to alarm off the same deviation. Right now, you can actually see the individual is 96, so a little bit cooler than the average, which is fine. They're not going to alarm. But the idea behind the average is every hour or so, you take a new sample, so you just take a new picture, and you update the average to account for discrepancies throughout the day. So when you take a new photo, what will happen is the oldest photo will be thrown away by the camera, and the newest photo will be stored, and the average sample will actually change based on the new photo, so that you're alarming off of a consistently changing value instead of just a threshold where you might miss on a cold day quite a few people, or over alarm on a hot day if everyone's appearing hot. So here's an example of our screening solution with the A400. It is a manual process, right? So even though our A400 does have RTSP and ONVIF, which makes it easy to connect to VMSs, the process of collecting the samples and verifying that someone is in the frame, not wearing sunglasses, and is the correct distance from the camera takes human intuition, right? Or programming additional software that does not come with our cameras. So as you can see in this example, the individual, the girl, is 3 to 6 feet from the camera. The area box in the screen or the computer is around her eyes to measure the canthus of the eyes, and it's automatically looking for the hottest spot within that region, and then alarming probably off of a deviation from a population sample or average. Now, this operator doesn't need to do anything. The camera will automatically alarm. You can alarm through a digital output, or you can alarm through an audible alarm, or you can alarm through ONVIF, or even I think I covered that, or even have the alarm show up on the screen for the operator. But what he's doing is, one, verifying that the box is around her eyes and that she's in the frame, and two, that when the sample needs to be taken, he's clicking a button to take a snapshot to update the sample. So these are IP cameras, and they are manually operated out of the box without additional software to verify that someone's the right distance, not wearing glasses, and the right height. But because they're IP cameras, you can use multiple web browsers. So they're configured simply by typing the IP address of the camera into a web browser, and then the configuration page and the live image appear. Now, hypothetically, if you have a computer, you could connect multiple cameras to an Ethernet switch and connect that to your computer, and you could view multiple cameras and operate multiple cameras at the same time. The only issue with that would be if there is high flow, high traffic, it might be difficult to make sure that you're looking at all the same screens simultaneously while people are trying to be screened. These cameras are also PoE, so they can be powered over Ethernet. Typical configuration of the A400, which is the best elevated skin temperature solution that ADI can offer, are as follows. Below is the part numbers. So you have either the thermal core, the A400, or the A700, one or the other. And then you need to get the smart sensor configuration. This just makes the core a smart camera. It doesn't add any additional benefits. With the core, you need to buy a lens. So this is a parted out system. We recommend the 24-degree lens, but you can get a 42-degree lens or a 14-degree lens. Then the screening mode software that I was talking about that does the running average and deviation alarming approach is the advanced smart sensor configuration. So you need that to get screening mode. Just to reiterate, screening mode does have a black body compensation algorithm in it, but you still have to buy a black body and put it in the field of view if you want to use that algorithm. It can be used simultaneously with screening mode. So you could be doing both the running average and be using the black body compensation. It also can come with a visual camera. I do recommend the visual camera. If there are any software updates, they might use the visual camera, as well as it helps identify which individual might have had the elevated skin temperature. And then lastly, the accessory kit. The accessory kit's going to come with an M12 to RJ45, so you can connect and configure the camera. It's going to come with an M12 to pigtail in case you want to use the digital input or outputs. It's also going to come with a PoE injector and a 2-ball mounting joint so that you can mount the camera on a desk, on a wall, wherever you'd like to, but it's not the same as a tripod. Some features of this include RESTful API, RTSP, ONVIF, and so forth. The only difference between the A400 and the A700 is pixel resolution. So the A700 does have 4 times as many pixels as the A400, but it is also a more expensive option. However, as we discussed earlier, if you are trying to identify the canthus of the eye, the inner eye or the tear duct, having smaller pixels helps tremendously, so you can monitor from a further distance using the A700. One last thing, we have been doing elevated skin temperature monitoring for over 10 years, so a lot of the people who have just jumped into this or are claiming they have solutions that might not work, this does set us apart from them. Additionally, we are registered with the FDA with a 510K, and we're produced in Sweden, so we do pass a lot of the checks that some of the customers have asked. Other than that, here's my contact information. I'll pass this off to Josh with ADI, and then we'll answer some questions.
Yeah, thanks, Jake. Really appreciate the presentation that you put together for us and everybody there at FLIR. I also like to say thanks to Mike Maston. Mike's done a great job putting together these webinars, and that way we're getting a little more knowledge while we've got maybe some downtime or while we're working at home to try to expand some of the offerings we have for our customers.